Hello everyone, and welcome back to another video where we are going to be covering the basics of derivatives. But before we get started, you can skip this intro bit if you just want the derivatives. I was actually hesitant to make this video, and the reason for that is because by making this video, I felt like I would be making content really just for the views rather than making it because I was genuinely interested in making it, right? But what changed that ultimately was the fact that people at school came up to me multiple times, same and different people actually, and they asked me to make an intro to derivatives video, basically, because they were learning that on the first or second day of physics, which is how physics C goes. Quite fun. But then they asked enough, and I guess I'm finally saying, okay, fair enough, I will make a video. So this one is for y'all. Y'all got me interested into making this. So, let's get the show on the road, shall we? What is a derivative? What is it? Conceptually, it's just the slope of a function at a point. It's just how steep it is at any given point. So I have a couple functions that I drew down here, right? I copied from Desmos. But you see this, nice little cubic function right here. I mean, you can just kind of see how steep it is visually, right? Like this point right here is obviously, steeper than, say, a point right here, or a point that's balanced. If I put a ball here, ideally it wouldn't move, but if I put a ball here, it's going to roll down the hill or down the function, quite fast. Or if I put a ball here, it's going to roll, not as fast. So conceptually, a derivative is just how fast a function is changing, or in other words, its slope, at any given point. Mathematically, the way we would define this, you can skip this part if you're just interested in the power rule, but mathematically the way we would do this is say, well, I have a point here, say, and a point here, and I'm going to draw a line between these 2 points, and the slope of that line, in the limit as one point approaches the other, the slope of that line is just going to be the derivative itself, how steep that function is at that given point. But I'm not going to get into that too much in this video. Rather, I think it would be more of use to have something going over the power rule, rather than going over the formal definition, which you aren't really going to use hardly ever, actually. But, it still does need to exist. But let's go on to the thing that you're actually going to be doing most of the time with derivatives, and that is called the power rule. So power rule. With great power does come great responsibility. And I'm just going to write the formula straight up, and we're going to kind of dissect what this means. So the formula for the power rule is the derivative, this operator right here, or that symbol right there, this d over dx. The derivative of some x to the nth power is just going to be equal to n times x to the n minus 1 power. There might be a lot to take in at first, but let's just kind of break this down real fast. What we're effectively doing is just taking this n here, making it a coefficient instead of an exponent, and then just subtracting 1 from the exponent up here. So let's maybe do a couple of examples for that to really, sink in. So say we have the derivative, right, of, say, x squared, right? According to the formula, what we're going to do is take this 2 right here, and we're going to make it a coefficient. So we had our x squared, but now that 2 up there is going to be a coefficient, so I'm going to write 2. But then, what does the exponent become? And the answer to that is answered by this n minus 1 thing right here. So you'll see that our n, in this case, is just 2. So, meaning that our exponent is just n minus 1, which is just going to be, 2 minus 1, which is 1. Meaning that whenever we have an x here, well, it's just going to be to the first power. So I'm not going to write that because the 1 is implied. And our answer is just going to be 2x. Let me do a couple more examples just to kind of drive the point home. Say I have the derivative of 3x plus 1. Well, according to the formula, we actually don't know necessarily how to do one big chunk like this because, well, we know how to do it for 1x, but not necessarily, 3x plus 1, right? And the way we deal with this is note that the derivative operator right here. So whenever we take the derivative, whenever we're adding two things inside it, we can, in a way, distribute it. So without getting too caught up in details on how it's a linear operator, we can just say this derivative right here, let me draw a line, that derivative right there of 3x plus 1 is equal to the derivative of 3x, and then plus the derivative of 1. And it's because of this that we can evaluate expressions like this, using the power rule. But it may not be 100% clear yet how we're going to apply the power rule, because in this example right here, we had x squared, but the coefficient in front of there was just 1, right? So how do we deal with coefficients like this 3 right here inside the derivative? And the answer to that is actually just, well, it's quite a simple answer. We just move the coefficient outside of the derivative, right? So this derivative of 3x, for example, is just going to be 3 times the derivative of x, and then plus the derivative of 1. And now we're kind of in a better position to actually apply the power rule. So let's do that real fast. What we have right here is an implied 1 above the x, right? Because it's just x raised to the first power. So what we're going to do, I'm going to zoom out a little bit, kind of running out of room. So what we have here then is going to be 3, but then this derivative bit, we're going to bring down the 1, and then we're going to multiply by x raised to the what power? Well, it's going to be n minus 1. And our n in this case is just going to be 1. So it's going to be 1 minus 1, which is 0. Remember that x to the 0 power is just going to be 1. That's just 1 right there. And then plus the derivative of 1. I'm going to tackle that in a slightly different way, actually. So let's just simplify this on the left, and then we'll deal with the derivative of 1 really fast. So we have 3, and then it's just 3, and then times 1, which is just, 3. So this whole thing right here, I will erase this bit right here. This whole thing right here is just going to be 3. And then plus this next bit. But what is the derivative of 1? Actually, for that matter, what is the derivative, so d over dx, of some constant c, of 1, 2, 3, pi, 7.8 or 9.8, negative 9.8? What is the derivative of a constant? And my answer to that is actually not necessarily going to be use the power rule, but just look at it graphically. So if we were to graph, say, I don't know, y equals 1, right? The graph is going to look something like this if those were our axes. It's going to be a straight line. I can't draw a straight line, but you get the idea. Let's just think about this, just conceptually for a moment. What does the derivative measure? Well, we said at the beginning of the video that the derivative is a measure of the slope of a function, how steep it is at a given point, or how much it is changing. And when we look at a graph like this, you see that, it's a flat line. It's not changing. If I put a ball on a flat line, if I put a ball on like a flat desk, it's not going to move as long as it's, not, slanted, right? The flat line isn't slanted. It's not changing at any point. I can plug in any value of x, and I'm going to get the same output. And that right there is just going to be 1. So the rate of change of a constant is really just 0 because it is not changing. So the derivative of some constant, I should specify, is just going to be 0. So this right here, we have a 3 plus the derivative of 1, which is just 0. So the derivative of 3x plus 1, that right there is just equal to 3. But let's think about this a little bit more, because conceptually we said that the derivative is a measure of the slope of a function, right? So let's think about the slope of a line real fast. We know that in slope-intercept form, y equals mx plus b, that the coefficient in front of our x is just going to be the slope for any given line. And if the derivative measures slope, then the two should equate. And indeed, that is what we find. We find that this 3 here is the exact same as that 3 here. It's a measure of that line's slope, just how steep it is or how much it is changing. And what's interesting about it is that it now even makes more sense that the derivative of 1 is 0. Because if you add, 1 or 2 or 30 for that matter, to any line, the slope isn't going to change. How steep that line is going to change. The y-intercept will change and the x-intercept will change. But the slope of that line right there is not going to change just because you bumped it up or down. And that's true in general of, functions in general, because the derivative of a constant is just 0. So let's go over maybe a couple more examples, and then we can go on to some more fun graphs. So let me actually rewrite the power rule right here. So d over dx of x to the n is equal to nx to the n minus 1. Okay, now let's say we want to, I'll put this in a little box up here. Let's say we want to differentiate, this is going to be a longer one, but differentiate x to the third over 6 plus x squared over 2 plus x plus 1. Say you want to differentiate that. I'm going to oh yes, I'm a YouTuber, I get to do this now. You should pause the video. Sorry, you should pause the video and try this on your own. You should do that before I solve it. I'm sorry, it feels so weird to say that. I feel like I'm usually hearing that. Anyway, let's actually get evaluating this, shall we? I'm going to split the derivative into the derivative of each component, right? So I'm going to say this is equal to the derivative of x to the third over 6, and plus the derivative of x squared over 2, plus the derivative of x, and then plus the derivative of 1. Straight off the bat, we know the derivative of 1 is 0. We established that. And what we're going to do next is just move these coefficients outside of the parentheses and outside of the derivative. So, in doing so, let me scroll down. In doing so, we find that this is equal to 1/6 times the derivative of x to the third plus 1/2 times the derivative of x squared plus the derivative of x. There's an implied 1 there, but we don't really care about that. So now all we have to do is just apply the power rule in each of these cases. So in this case right here, we see that n is equal to 3. In this case, we see that n is equal to 2. In this case, we see that n is equal to 1. So let's bring down the powers of each of these real fast. So we know that this right here is going to be, we have our 1/6 still, but we're going to have a 3. Over here, we're going to have our 1/2 still, but we're going to have a 2, because our n is 2. And then right here, we're going to have an implied 1, right? So 1. And then subtracting 1 from each of the exponents, we find that we have an x squared. And then we have just an x. And then we have just, times x to the 0, which is just going to be 1. And adding all these together and simplifying the fractions, please simplify your fractions, we find this is going to be x squared over 2 plus x plus 1. And that right there is our derivative. And this is the part of the video where I'm going to kind of connect this to what we're doing in physics. One of the most important things or applications of the derivative is the fact that, it does the following. If we apply the derivative to, say, position, right? If we have a function of our position, and through this derivative, what we find is that the result is our velocity. And if we apply the derivative again, what we end up with is our acceleration. So by applying this derivative to each function, right, by applying our derivative to position, we get velocity, and by applying the derivative to velocity, we get acceleration. And the reason why this is so important, at least in physics, is that we can take a graph like our parabola right here. That parabola might be the result of us, throwing something, right? Or dropping something off a roof. We know that whenever we have a parabola, or whenever we throw something, it's in the shape of a parabola. So if we differentiate that, we find our velocity. And in general, a parabola is going to have something, it's going to be something in the form of x squared. But what we established is that if we differentiate that, what we're going to get is like a 2x. So what this actually tells us is that based off of our position, we can find our velocity, yes, but our position was parabolic, yet our velocity is not parabolic. It is a straight line. So let's just think about this one more time and say, okay, let's differentiate this one more time and let's find our acceleration. So if we differentiate this 2x, right? This 2x, we apply the derivative. What we're going to get is just 2. So what we've just found might not seem very important at all, but what we've just found is that given a parabola, given the fact that whenever I throw something, the shape is generally a parabola, what we've just shown is that our acceleration right here, because you've seen that you would go from position to velocity to acceleration, what we've just seen is that this right here, the fact that that x squared becomes just a 2 shows that our acceleration is just constant, which implies that the force of gravity is constant. And this is effectively where derivatives shine in physics, amongst other things as well, of course. But this is kind of where you first see it. So what started, when you probably first started hearing about this stuff, what started as just average rate of change to get from position to velocity has now become instantaneous change at a point. What has become what was change over an interval is now change specifically at a point. And by applying all these things together, what we can find is acceleration when we're given position and vice versa, but the other way around does require integrals, which is going to be another video probably. So that, I think, is going to actually conclude this little video about derivatives. I hope you all found it, first and foremost, helpful, but secondarily, I do hope you found it somewhat entertaining. But at any rate, thank you so much for, any rate, that was unintentional. Anyway, at any rate, thank you all so much for watching, and I will see you in the next one.